Well, now we'll discuss about the series and parallel connection of resistances. The resistances can be connected in series, parallel, or they can also be connected in star, delta, or in some other complex forms. But the thing is that all the complex forms can be reduced to the series or parallel form. So here our job is to calculate the equivalent resistance of the series connection. So let us consider this circuit. This circuit has three resistances, R1, R2 and R3. They are connected in series. How you will know? The resistances are said to be connected in series when they are logically forming a chain-like formation. You see that they are forming a chain-like formations, so that the current through them is the same. The same current flows through all these resistances. Here it is connected to a voltage source V. This is the voltage source applied across these resistances, and they are said to be connected in series. Now our job is to calculate the equivalent resistance of these three. So equivalent resistance, what is the meaning of equivalent resistance? That is when these resistances will be replaced by this equivalent resistance, then the state of the circuit will remain the same. That means when the voltage supplied is V, the same voltage is here, then the same current will flow here, what it was flowing. If I current was flowing here, then the same current I will flow in this circuit, which is the resistance R equivalent. And what should be this R equivalent? That we have to find out here. Now this voltage is V1 and voltage across this resistance is V2, voltage across this resistance is V3. That you can connect a voltmeter across this and you will note down the voltage. You will connect one voltmeter across this resistance, note down the voltage, and similarly connect voltmeter here, note down all these three voltages V1, V2, V3, and you will observe that V is equal to V1 plus V2 plus V3. These three voltages, when they will be added, will be equal to this supply voltage. Now what is the relationship between V1, I and R1? All these resistances, they will also obey Ohm's law. So V1 is equal to IR1, V2 is equal to IR2, because the same current I flows through all the resistances, and V3 is equal to IR3. We'll write down here V1 is equal to IR1, V2 is equal to IR2, and V3 is equal to IR3. So we'll put all these values here. So V is equal to IR1, V1 is equal to IR1 plus V2 is equal to IR2 here, plus V3 is equal to IR3. Now this voltage V from the equivalent circuit. You can observe that this circuit also obeys the Ohm's law. So V is equal to I R equivalent. So you can write I R equivalent is equal to, taking I common from all this, you can write it like this. So cancelling I from both sides, we find that R equivalent is equal to R1 plus R2 plus R3. Hence, in case of the series connected resistances, their equivalent is simply equal to the sum of the resistances. So we can, in this way, we can find the equivalent resistance. So if these three resistances will be replaced by R equivalent, the same current will flow through the circuit. Let us now explore the parallel connection. The resistances are said to be connected in parallel when one end of the resistances are connected together, forming one terminal. Here R1 and R2, one side are connected and forming this terminal A, and the other end of the resistances are connected together and forming another side or another terminal, that is V. Now we can say that R1 and R2 are parallelly connected. And now here we are supplying the voltage V across these two resistances. Now we have to find the equivalent resistance of these two resistances. Equivalent resistance means if that resistance will be connected in place of this R1 and R2, that means this parallel circuit from A and B will be removed, and in place will connect a equivalent resistance, that is of value Re. Then the condition of the circuit will remain the same. That means when the voltage V was connected in this circuit, current I was flowing through the circuit. Then in this case also, after replacing with Re, the same voltage source is connected here. Then the current that will flow is I. So now we have to find this Re. What should be the value of Re? Now consider this resistance, two resistances R1 and R2. The voltage across these resistances is the same, V. In case of series resistance, what happened? The current that was flowing through the resistances was the same. If the current flowing was I, then I current that was flowing in R1, and that same I current was flowing in resistance R2 also. But the voltage between these two were different. Here the voltage across R1 was V1 and voltage across R2 was V2. But in this case, the current that is flowing through the resistances are different. That means if it is I1, then this current is I2, and the voltage between the resistances is the same, that is V. V voltage is applied across R1. This voltage will appear across R1 and R2 both. So now the Ohm's law will apply individually to R1 and R2. What the Ohm's law states? The voltage V is equal to I1 R1, or I1 voltage V equal to I1 R1, or I1 is equal to voltage V divided by R1. So you can write I1 is equal to V divided by R1. V is the voltage across this resistance. Voltage across this resistance is same as this voltage. They are directly connected. And I2 is equal to V divided by R2. Similar to this, voltage across R2 is V and the current flowing through it I2. So I2 will be V2 divided by R2. Now you can say that I, the current in the main branch, that current will be sum of I1 plus I2. So I is equal to I1 plus I2. Now putting the values of I1 and I2, I1 is equal to V divided by R1 and I2 is V divided by R2. This is I. This is I. So we can now I. What is I? Thus in the equivalent circuit, this I will be equal to V divided by Req. So I is equal to V divided by R equivalent. The same Ohm's law is applied here. So I is equal to V divided by R equivalent, Req. That is equal to, taking V common, 1 divided by R1 plus 1 divided by R2. So V will cancel out. So we'll finally get 1 divided by R equivalent is equal to 1 divided by R1 plus 1 divided by R2. And this is the equation that relate R equivalent with R1 and R2. Given the values of R1 and R2, we can calculate R equivalent from this equation. If there are more resistances connected in parallel, similarly we can write that 1 by R equivalent, that is equal to 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. That depends on the number of resistances in parallel. Let us further analyze the series and parallel connection, and here we will compare the depend on these two types of connections. In case of series connection R1 and R2, what is the equivalent resistance of R1 and R2? Let it be R EQS, as we have taken for series, EQ for equivalent. So R EQS is equal to R1 plus R2. So these two resistances can be replaced by this R EQS. This is R EQS, and this you can see that this R EQS is equal to sum of these two. So R EQS is bigger than both R1 and R2. But here in this case, when they are parallel connected, let us see, let their equivalent resistance is R EQP. So we can replace this by, this is the equivalent resistance R EQP, P for parallel connection. What will be this resistance? This resistance and these two are, they are related by this equation, 1 by R EQP is equal to 1 by R1 plus 1 by R2. That what we just learned. So simplifying this, what we can find, that is equal to in the denominator it will be R1 R2, that will be the LCM. So in the numerator it will be R2 plus R1. So you can write that R EQP, that is equal to R1 R2 divided by R1 plus R2. This is algebra. So what is this value? We can divide this by R1 R2. So we can divide this by R1, so to say. Then in the numerator it will be like this. In the denominator also we will divide this by R1. So it will be R1 plus R2 divided by R1. That is equal to R1 will cancel out. It will be R2 divided by R1 by R1. We'll do partial fraction. It will be R1 by R1. It will be 1 plus R2 by R1. Now what will be this value? You can see that R2 and R1, they are all positive. So this denominator will be greater than 1, because this will be added to 1, means it will be greater than 1. When R2 will be divided by a number that is greater than 1, that means this number will be less than R2. So that means R equivalent less than R2. Similarly, we can again write that equation, R equivalent P, that is equal to, we can divide this equation again by R2. Previously we divided by R1, here we will divide by R2. So it will be R1 R2 divided by R2, and the denominator is also be divided by R2, because if numerator is divided by R2, denominator should be divided by R2, otherwise its value will be different. To keep the value same, we have to divide both numerator and denominator by the same number. So here we have divided by R2, previously divided by R1 plus R2 divided by R1, divided by R2. So R EQP is equal to R2 will cancel. In the numerator it will be R1 divided by, in the denominator just separating, it will be R1 divided by R2 plus R2 by R2, it will be 1. Here also you can see that this number is greater than 1. When the denominator is greater than 1, that means this fraction will be less than R1. R1 will be divided by a number which is greater than 1. That means this fraction will be less than R1. That means this fraction is R EQP. So R EQP less than R1. So from this we can say that R equivalent P, that is both less than R1 and R equivalent P less than R2. So when we will connect the resistances in parallel, their equivalent resistance will be less than both the resistances. So what we got here, the equivalent resistance is always less than the individual resistances. Here we have shown it for 2 resistances, for 3 resistances, R3, R4, etc. For all these resistances connected in parallel, their equivalent will always be less than any of the resistances. That will be less than R1, less than R2, less than R3, less than R4. Okay, that's all today, and we'll discuss more next time.